We introduce Mimicking-Bench, the first comprehensive benchmark designed to support generalizable humanoid-scene interaction skill learning through the mimicking of human references. The past decade has seen remarkable advancements in humanoid robotics. However, existing benchmarks for humanoid scene interactions either exclude the use of human knowledge or focus on small-scale, specific demonstrations collected through expensive teleoperation. To fill this research gap, we present Mimicking-Bench. We integrate a large-scale and diverse human skill reference dataset and propose 6 humanoid scene interaction tasks: sit chair, lie bed, sit sofa, lie sofa, touch point and lift box. We first introduce a large-scale human skill reference dataset, followed by a retargeting module that transfers human motions to humanoid models for animation generation. A motion tracking module then simulates realistic motions based on these animations, producing skill demonstrations. Finally, an imitation learning module trains humanoid agents to handle unseen scenarios using these demonstrations. We have integrated a large-scale human skill reference dataset for the 6 tasks. For sitting on chairs and lying on beds, we generate reference motions using Unizy, which takes chains of contacts as input and outputs humanoid motions for the AMP robot. For sitting and lying on sofas, we use Roam generate human motions. For the tasks of touching points and lifting boxes, we acquire human skill references from the existing motion capture dataset Core 4D. Mimicking-Bench has a wide variety of objects and skill references, with significant diversity in object scales. By leveraging this dataset, Mimicking-Bench fosters studies on the generalizability of methods to changes in object geometry. To connect human skill references with humanoid animations, the motion retargeting module transfers motions from a human skeleton to a humanoid skeleton. These methods can be categorized into 3 types: optimization, copy rotation, and optimization with skeleton shape alignment. Optimization aims to accurately recover joint positions, tolerating some loss in joint angle fidelity. Copy rotation directly replicates joint angles. Optimization with skeleton shape alignment first adjust human skeleton bone lengths to match the humanoid skeleton, followed by optimization. We evaluate the performance of combining these 3 retargeting methods with optimal designs from other modules. Regardless of whether the human reference motions are physical, the retargeted humanoid motion is unphysical. To generate physical humanoid skill demonstrations and corresponding action sequences of the animation, we apply a tracking module to the motion animations. For the tracking module, we benchmark HST with additional reward constraints and a simplified version of PHC without the suggested composer that combines multiple policies. We ablate the humanoid motion tracking algorithm in our pipeline. The imitation learning module aims to train a generic humanoid agent using humanoid skill demonstrations. The visual observations of the humanoid include color images from 4 egocentric cameras and their corresponding depth images, combined with an elevation map. We compares the performance of combining 2 imitation learning methods HIT and ACT with the optimal retargeting and tracking algorithms. We also compare 2 common designs color images together with depth images and only elevation map for visual observation. The comparison between 10% and 100% training data highlights the impact of data scale on performance. The best combination on our tasks takes optimization as retargeting method, HST for tracking and ACT for imitation learning. Additionally, we evaluate a vision-based reinforcement learning (RL) method which learns entirely through environment exploration without human references. RL performs significantly worse with poor physical plausibility. Finally, we show a significant performance improvement as the data scale increases, particularly for objects of extreme sizes. This demonstrates that large-scale data is crucial for training robust models.